I'm not sure who is the boss, or are we self-organized?
So, welcome back. The first talk will be given by Anton Alekseev from University of Geneva on Verisoro Hamiltonian spaces. Thank you, Anton.
Thank you. Yeah, I would like to thank the organizers for an opportunity to speak here. And of course, it's an enormous pleasure to see you all in person and some of you online, but still the grand majority in person. Of course, all those years of global Poisson, that was nice and exciting, but I think that's also a great thing to be here together. One more time, congratulations to the prize winners 2022. So I'll be speaking today about the Verisora Hamiltonian spaces, and this is a work in progress with Eckhart-Meinrenken. And in progress part, you will see in some of my statements or so-called theorems, you will see that they at the moment lack detail. Also, I apologize, I'm not sure how visible are my slides. So, but please complain if you cannot read stuff, because then I will read or maybe rewrite it for you. Here, the idea is that in principle, I can modify those slides, but when I saw that they were not very visible, it was too late to redo 21 slides over 10 minutes. So kind of, we'll see how it goes. So here is the plan of today's talk. I will start with a relatively lengthy introduction, And I will be talking today about moment maps. Moment maps is one of the interesting parts of Poisson geometry, or you can say equivariant symplectic geometry. So I'll recall the standard definitions and some of the great results that probably most of you know very well, maybe better than me, about ordinary moment maps for actions of compact groups on symplectic manifolds. And then I will venture into infinite dimensional examples. And in fact, one of the infinite dimensional examples, these are Hamiltonian actions of the loop group or central extensions of loop groups. That's the theory which was developed about 25 years ago by Rankin and Woodward, and we'll revisit that theory. It has many great results. And then we'll be moving to the topic of today's talk. So what we call Virasoro Hamiltonian spaces, strictly speaking, this is a little bit of mismanagement of the language, because Virasoro is a Lie algebra over complex numbers, but we'll be talking about Hamiltonian actions of the central extension of diff S1. We'll come back to it, but basically when you want to move from finite dimensional group actions to infinite dimensional group actions, you have, of course, a whole zoo of infinite dimensional groups, but your first two candidates are central extensions of loop groups and central extensions of diff S1. So these are basically your first two choices. And the story of central extensions of loop groups, it started, as I said, more than 25 years ago. It still continues. And one of the prize winners, Yanis Loizidis, made fundamental contributions to this topic recently. But the story of diff S1 Hamiltonian actions, it looks like it's less studied. So I will try to say something about it, but it's basically in its infancy. So then one of the examples will be revisiting quadrant orbits of the Verisora action. This is actually an old story. So up to here, after this example, there is nothing new. I will be just reviewing basically some literature. That's a very interesting thing, this classification of Virasoro quadrant orbits. We'll briefly see some beautiful diagram. And then, so this is in color, some kind of new stuff that I want to talk about. So our conference is Poisson geometry and mathematics and physics. And actually this example of Virasoro Hamiltonian structures on the space of hyperbolic metrics, it is motivated by recent developments in physics. So these are quite mysterious and interesting developments, and we are trying to understand a very small portion of it, one should say. So apparently it comes from condensed matter physics, and then there is also a leg of it in what is called quantum gravity. There are many quantum gravities in 2 dimensions. One of them is called Untitled, and there people encounter some kind of interesting geometry of hyperbolic metrics, and that's what we try to interpret. And that will be this example. And then there will be also a relation to group-valued moment maps, and that's another result that I want to present today. And I will finish, let's say, there are many more open questions than solved questions, and I will try to review some partial results or some ideas or some open questions in the end, if time permits. So that's basically the plan for today. And now tell me again, do you really see the slides or not so well? Okay, good. So now the beginning, I hope it should be very pleasant, because moment maps, that's one of the things that motivate us to do Poisson geometry. It's very, very beautiful. It's one of the most beautiful theories in mathematics which exists. And let me remind you the standard setup. So we start with G, a compact connected Lie group. So the beautiful G is its Lie algebra. And we consider connected
compact connected G manifolds, so manifolds on which such groups act. And here is the definition of Hamiltonian G spaces. This is one of the most successful definitions in Poisson geometry. Of course, I don't know, right? There is just a definition of Poisson manifolds, which is fundamental, but this is maybe at par with that definition. So this is the starting point of equivariant symplectic geometry. So we consider the following set of data. We have a G manifold M. We have a G invariant 2 form omega on M, and a map from M to the dual of the Lie algebra. And we say it's a Hamiltonian G space if it satisfies the following 3 axioms. So M omega is symplectic, which means, of course, that omega is a closed 2 form, and that the kernel of the induced map from omega, from the tangent space to the cotangent space, the kernel is trivial. So in other words, omega is non-degenerate. And then there is the moment map equation. Let me try to modify the slide. So one idea was to use technology and to profit from the fact that here we cannot give chalk talks in this room. So, okay, right. So that's probably the most important equation, the moment map equation. And finally, let me take a restrictive definition. Of course, sometimes it can be relaxed. We want the moment map to be equivariant under the action of G on the manifold and the coadjoint action on G star. In fact, that's an important part of it, because later in infinite dimensional cases, we're going to be discussing or negotiating the equivariance condition. So that's important to know what kind of equivariance we want. So why this theory is so famous, or why this definition is so successful? Because it has many beautiful consequences. Let me list 4 of them. Of course, there is famously reduction. You take a pre-image of some good point in G star under the moment map, and you take a quotient by the coadjoint stabilizer G psi, and the resultant space is symplectic. Of course, there is a big story. How good is the space, whether it's a manifold or orbifold, or whether it has more serious singularities. But it's in all those categories, it's a symplectic space. So then there is famously convexity. So maybe I should also start mentioning big names in our field. So the Marsden Weinstein reductions theorem, and for convexity, this is in the abelian case, Atiyah, Gilman, and Sternberg, and then the Curwen's theorem in the non-abelian case. So we take the image of the moment map and we divide it by the coadjoint action. It naturally sits inside the quotient of G star by the coadjoint action. And surprisingly, it turns out that this quotient space, in which a priori maybe you don't have a notion of convexity, but this thing actually sits as a polyhedral cone in some vector space. So then inside it, there is an image divided. So here there is an image divided by a joint star action. And now it does make sense to say that it's convex. Of course, in the abelian case, the coadjoint action is trivial. Then there is no problem with the notion of convexity. But surprisingly, even in the non-abelian case, there is a notion of convexity, and it works to the great effect. So the third big theorem is localization. And of course, localization is also a huge field, but maybe in particular, the following oscillatory integral that we have here, this I of x. So integral with the Liouville measure of the exponential of the pairing of mu with some element x of our Lie algebra. Let me let me say that X is in G, can be what people say localized to the fixed point set of the action of the maximal torus on M. Note that this is an action of the torus and not of the whole group G. So in particular, this fixed point set may consist of many connected components, and so the integral reduces to some integrals over those connected components. I don't make precise what are the corresponding localization contributions, because I just want to indicate that there is this big result. Of course, the easiest thing is when this set MT consists of, which is just a finite set of points. So then those results, they are most impressive. But of course, there are also other geometric situations. And finally, the famous Gilman-Sternberg quantization commutes with reduction principle, which also was mentioned today in presentation of the prizes. And here I won't be speaking about it because it would take too much time. So there are great consequences of the definition. And I don't mention on a more technical side, there is a curve and surjectivity result, but so there are many big things. So it's a kind of wonderland, this theory of moment maps. Now there is a natural question: can you generalize this theory? Can you extend it to some other cases and keep all the good consequences, right? Typically, you would expect that the answer is no, right? Because if once something works and it just produces miracles, kind of should it produce miracles again? But it turns out that there is at least one example, which is actually infinite dimensional, where basically the same miracles with some modifications happen. And so there the setup is as follows. So now you take G to be compact connected, and let me make it more precise, simply connected Lie group. So then there is a canonical center extension of the loop group, the group of maps from the circle to G by S1. In order to define this canonical center extension, you need to fix an invariant scalar product on the Lie algebra. So, and this theory was developed, as I mentioned already, about 25 years ago by Meinrenk and Woodward. And then the development of trying to figure out whether those big results, they hold, it took, one can say, in some way, a couple of decades. So it was like already some easier results we obtained from the very beginning, but then it turned out that basically everything generalizes. So the Hamiltonian actions of this central extension of this object, they are almost as good or as good, just in some way more exciting and interesting than Hamiltonian actions of compact groups. So let me give you a little bit of, just remind you a little bit of how it works. And you know, when I was preparing this talk, I remembered that I actually gave a talk about this theory in a Poisson conference in the year 2000, which is probably one of the first big Poisson events in Lumini. Of course, that time I was much younger, so it brings some kind of nostalgic memories of that event. So, okay, but never mind. So on a little bit more on the technical side, so the Lie algebra of LG hat, as you see here, so this is the loop algebra, the maps from S1 to the Lie algebra G, plus the central part. We do it over reals, so plus a copy of R. And the dual, what is the dual? So you can realize the dual of those maps using the scalar product as one forms this value in G. Of course, here I'm not making precise my topology. So this is, of course, not the full dual. That's what is called a smooth dual. And still, the dual of R is again a copy of R. So that's already going to be a target of our moment map. So one forms on the circle with values in the Lie algebra plus real numbers. What is interesting, what happens with the coadjoint action? Remember, like I said, that the coadjoint action is a little bit negotiable. Now we should say, what is the coadjoint action? So the action of the loop group or a central extension of the loop group on this space, the smooth dual of LG hat. And it turns out that the central circle acts trivially anyways. So you only need to say how LG itself acts. And it turns out that this coadjoint action is something that people know very well. Either you can say in the theory of principal bundles or in physics. So this is the gauge action. So A is one form with values in the Lie algebra, and G is a function on the circle with values in the group. And that's what happens. Here, I pretend that all my groups are matrix groups. In order to write, otherwise it would be too complicated in the notation. So you conjugate A by G, and this resembles of ordinary adjoint or coadjoint action for compact Lie algebras, but then you add this interesting piece with a coefficient which depends on what is called the level, because you have here this copy of R. So this K is a value, takes values in that R. So we get some kind of affine action, which is called the gauge action. And now we can give a definition of a Hamiltonian LG space at level K. Now we fix that number K, and for each number K, we get an interesting definition. And for us, we will always be assuming that K is non-zero. If K is zero, that's a different game. So again, we consider spaces. Of course, now they will typically be infinite dimensional spaces. So we have an action of the loop group, LG. We want a two form, which is LG invariant. And we want a moment map with values in this smooth dual. So that's basically the same definition. I just replacing item by item. Maybe one important thing, if you want a well-behaved theory, you want this map to be proper. So then the theory is really very, very well behaved. So now the axioms, they remain the same. So n omega should be symplectic, but here, since it's an infinite dimensional gadget, usually we're not going to dive into it, but just to tell you, typically we have to weaken the axiom, say that the map induced by symplectic form is injective. It's usually difficult to require it to be surjective. This is called weakly symplectic. The moment map equation simply remains the same. And now in this equivariance condition, of course, you want the gauge action instead of the naive coadjoint action for LG. So this K DGG minus 1, this is an important thing. I will tell you in a couple of slides why this is important to keep K to be non-zero. Yes?
Do you have like a specific requirement to add? Is that like a non-academic, that sort? What's that?
What is n? And yeah, it's you can say you can require it to be a Banach manifold. Right.
You can also regard the Hamiltonian action. You can see it as looking at the action induced by the Lie algebra, infinitesimal action, and has to be by Hamiltonians. No? I was wondering if in this case you can rephrase the definition as in the finite dimensional one.
Probably. Of course, there I don't quite remember what would be the integration criteria, right? Suppose you induce it, and then would it necessarily integrate to an action of LG, right? For a compact group, that would necessarily integrate, but for LG, I don't quite remember. But you know, there would be, let's say, as we are stating it now, the definitions are basically the same, but maybe just one small warning. It's really easier to work with two forms in this infinite dimensional setting. But if you want to do an analog of Poisson geometry, so that would be in some way much more tricky. Because there on this infinite dimensional setup, you may argue whether these are really Poisson brackets, or if you start thinking about domains of definition, maybe these are actually Dirac structures, and this question in some, let's say, in the important but still restricted situation of this LG hat star, it has been addressed, but I'm not sure that there is a good formulation on the Dirac, infinite dimensional Dirac language for that. So now let me give you a key example, and actually we'll be later mimicking this example in our DFS1 story. So if you take sigma, a compact connected oriented to manifold, and for simplicity, let's assume that the boundary of sigma is a copy of a circle. Of course, we can in principle consider more complicated surfaces. So then here is an example that one can build. One considers one forms with values in G, or in other words, connections on the surface, and one imposes the condition that they're flat, so the curvature of A is 0, and we divide by the gauge action now on the surface. But for the gauge transformations, for the gauge group, we require G to be equal to identity on the boundary. Usually, I think when you kind of, in the definitions of modular flat connections that you usually see, you don't impose this condition, but now we do impose this condition. In fact, first of all, one consequence is that the resulting space is infinite dimensional, this N, and it carries a residual action of the quotient of the gauge group by this restricted gauge group where the action at the boundary is trivial. So actually this tells you what is the LG action. So now what are the other elements of the construction? Famously, there is a two form. It's the Atiyah-Bott form. You build it from integration over the surface and from the scalar product on the Lie algebra. It turns out that it gives you a weak symplectic form on that space. And the moment map for the LG action, so remember, it should be one form with values in G on the circle, and you simply restrict A to the boundary. So maybe just notice that here, all those constructions are quite intuitive and nice. And again, there will be some contrast with the more involved situation with metrics and with Virasoro in some slides from now. So this was one of the motivating examples why Meinrenken and Woodward wanted to develop this theory. And it turned out to be very, very successful. First of all, the reductions theorem works basically without changes. The spaces are symplectic spaces, and the singularities depend on how well or how nicely the stabilizer acts on the level set. So this doesn't change. Interestingly enough, there is even convexity because, again, somehow miraculously, the space of conjugacy of gauge classes in one forms turns out to be now a convex polytope called Weil-Alkov. So that's this space, and inside it is sitting the quotient of the image by the gauge transformations. So it again miraculously does make sense to say that it's a convex polytope, because you realize this space of gauge classes inside the target of the moment map as a piece of a vector space or as a piece of an affine space. So, so those results, they don't require other techniques, but it turns out that there is also localization and quantization commutes with reduction. So in the beginning, they required those group valued moment maps, but now we heard, let me refer to the work of Yanis Loizidis, who was doing this quantization commutes with reduction directly in the infinite dimensional setup that I've just described. But now let me say a couple of words about group valued moment maps, and there my introduction or whatever, my first review part will hopefully end. So here there is an interesting fact. So in the loop group, there is a normal subgroup. So you choose a point, let's say 0 on the circle, and you ask maps from the circle to the group to be equal to 1 at that point. It turns out to be a normal subgroup. So it's easy to check, but in some way we are lucky that it is the case. And we're not going to be so lucky in the Verisora case. So, and it turns out that on the target of the moment map on this omega-1 S1 of G, this action is free. So there is a normal subgroup and it acts freely. But then since the moment map is equivariant, it has to act freely on the space N as well. So this means that you can take a quotient, right? You see here the line above, that's the line from the definition, but now you can take a quotient. And since it's a quotient by a free action, it's a nice action, and the resulting space M turns out to be a compact finite dimensional manifold. And when you divide omega-1 by that action, the quotient turns out to be just a copy of your group. And the map actually is just computing a holonomy of a connection on the circle. So you end up with a kind of proxy of your finite dimensional situation. And this proxy is a finite dimensional manifold which carries an action of LG divided by omega G, which is again isomorphic to G. And it has a map phi to G. See, so you get some kind of finite dimensional story. So this was developed by Malkin, Meinrenken, and myself. And it turns out that also on this space omega-1, you can invent some kind of universal two-form sigma, which allows you to descend the symplectic form to the space M. It loses the property of being symplectic, but it's still a good proxy. So somehow all your structures descend to a finite dimensional proxy. Now, in terms of this finite dimensional proxy, for instance, you can formulate the localization result, because otherwise you see integrating over infinite dimensional spaces, who knows how it works. It might be somewhat risky, right, to state results or conjectures about those infinite dimensional integrals. But now on M, you can do finite dimensional integration. And here I give you some approximation of a theorem that I proved with Meinrenken and Woodward many years ago. And here you see you have something like a Liouville form, not quite a Liouville form, but something like a Liouville form. And here you have something which replaces the exponential. It's a character of an irreducible representation, now of a non-abelian group. And then the right-hand side is again a sum of connected components of a fixed locus under the action of some subgroup. Now it's not a maximal torus, it's some circle subgroup, and the circle depends on the highest weight of the representation you chose, but still the outcome is the same. You're getting some localization contributions, which might be points. Maybe just kind of one interesting remark about that old result. So before, remember, we had fixed points of the torus, and now we have fixed points of those circles. And there are examples where the fixed points of the torus are empty, but the fixed points of circles, they are non-empty. And there is still no conceptual topological explanation of those formulas. So these formulas, they give a somewhat different type of localization in comparison to the classical theory coming from equivariant cohomology, but we don't really know the concept. So the formula is there, you can compute things, but we don't know conceptually what's going on here. But okay.
The yellow hides the text, the purple does not make sense.
Sorry?
If you look there, you can see the purple, but not behind the yellow.
Oh, you mean no, but I think it very much, what I see on the screen is very much the same as, which part you don't see?
The part behind the yellow.
Maybe you say in the mic.
I don't know if this is just me or everyone else, but the purple, when you highlight in purple, we can see the text. When you highlight in yellow, that hides the text.
Okay, I will no longer use the yellow. You see, I just ban it. Thank you. Okay. So finally, so what I want to discuss today. So that's a similar story, right? So there is another group which has a center extension. So this is orientation preserving diffeomorphism of S1, diff plus S1. It also has a canonical center extension. Maybe here actually, I want to, diff plus S1 is not simply connected because it contains the circle itself, right? So it's actually somewhat more convenient, I highlight in purple. It's somewhat more convenient to consider the universal cover group of diff plus S1. So here, in principle, I should probably say, I should put this universal cover. So these are the maps from R2 itself with positive derivative, which are quasi-periodic. F of x plus 2 pi is f of x plus 2 pi. It has a Lie algebra, which are just periodic vector fields on the real line, or you can say vector fields on the circle. Now, maybe slightly more exotic for some of you, the dual of it, that's the space of quadratic differentials. So the sections of the square of the bundle of one forms, which we write as t of x dx square. Note that here dx square is not zero, just by definition. And why is that? Why is it a natural thing? Let me try to recolor into purple. I don't know whether it's going to work. Does it work? Yes. Okay, so, right. Okay. Okay, wait, one sec. See? Okay, so, right, that's because you have d over dx in vector fields and dx square in quadratic differentials. As maybe sometimes our students in the first year do, you cancel dx squared divided by dx, you get dx remaining. And so that's naturally one form and you can integrate it over the circle. So maybe more interestingly, so we have a center extension. So we expect to have some affine coadjoint action similar to the gauge action that we had before. And here is the formula. I don't know, probably many of you have seen it already, but if you haven't, I envy you. That's a really interesting and surprising formula. So a quadratic differential, so the first part of the transformation, that's just the coadjoint action. So what happens, right? The diffeomorphism group transports t to the point f of x, and since this is a quadratic differential, it multiplies by f prime squared. Now, what's the analog of the gauge term? Well, there is again this number c, which is the level, which is kind of the affine hyperplane in the dual. And then it's multiplied by this beautiful and horrible and very interesting expression, which is called the Schwarzian derivative. So that's instead of this dal, of course, very nice, but dal dgg minus 1. So that's the counterpart for the Virasora theory. So this is the third derivative divided by the first derivative minus mysteriously 3/2, second derivative divided by the first derivative squared. Again, I hope there are some people in the audience who see it for the first time. And I congratulate, I mean, okay, if you can forget everything else from the talk, right? That's a very nice and beautiful formula. Right. Now you can give a definition similar to what we were doing already, right? We went through it 2 times. We do it for the third time. We consider infinite dimensional spaces with an action of this group G, which is the universal cover of diffeomorphisms. We want to have an invariant 2 form, and we want to have a moment map with values in the space of quadratic differentials. Now, so we want this space to be symplectic in an appropriate category. And maybe here I want to start indicating. So I said it's a work in progress. We're not completely settled on the category. Probably that's going to be Fréchet manifolds. Probably Banach manifolds is not sufficiently good. So the category here is not completely fixed yet. So the moment map condition is the standard one. So nothing happens. And of course, we want the moment map to be equivariant under the affine action with the beautiful Schwarzian derivative. And we want C again to be non-zero, because C equals 0, that's a completely different game. So maybe, right, the right question now, I advertised that there are 4 big results, and here reduction would still be fine. To be honest, not much is known even of existence of other results at the moment. I will make some very short and cryptic comments in the end about localization, and maybe suggest that quantization commutes with reduction is not completely hopeless. Convexity, maybe it's not so clear it makes sense. So C. Now, what about examples? So I want to present 2 types of examples, and one is classical and very much studied, and still very interesting. Research on this example, or this set of examples, continues in literature. And then another example is sort of new. So of course, typically coadjoint orbits, that's an example of Hamiltonian spaces, even in the finite dimensional situation, and also for loop groups. And now, so there are many people who studied Verisoro coadjoint orbits. In the beginning, it didn't have that name. So Lazutkin, Pankratova, they studied what is called Hill operators. So they didn't talk about coadjoint orbits. And then there were foundational works of Kirillov and Siegel. And then Witten popularized this topic in physics. And then there are tens of other references. So now remember that our action is on quadratic differentials. And so you see this, this is a kind of scheme. This is a classification. What you see on the screen, this is a kind of classification of coadjoint orbits of Verisora. You see, it's intricate and interesting. And you have this horizontal line, which corresponds to Verisora coadjoint orbits, which pass through constant t's. So you have t of x, and you can say, let me start with t just being a constant. And that's this horizontal line. And on that horizontal line already, there are many things happening. So there are so-called hyperbolic rotation 0 orbits. That's the best behaved orbits with t negative. So these are probably the preferred, the best behaved orbits. So, and there are elliptic orbits where t is positive, and they're both isomorphic to diffeomorphisms of S1 divided by S1. So the stabilizer, the typical stabilizer is S1. But then there are those points n squared over 24. So these are exceptional orbits, and among them, like I would say, there is a huge amount of literature about one of them. So like probably more than half of the literature is about this point, 1 over 24. So this is called the Teichmüller orbit, and it turns out to be isomorphic to so-called universal Teichmüller space, which makes contact to other parts of mass. And this is isomorphic to diff S1 divided by SL2R. And then for other orbits, there would be some covers of SL2R as stabilizers. But then you see, mysteriously, there are other families which are attached. So when we have an exceptional orbit there, this set of quadrant orbits, it branches. And there are those mysterious hyperbolic orbits of higher rotation numbers. And basically, there is almost no literature about it. So people write some representatives there, but it's not well investigated what's going on there. And just to mention, there are also some parabolic orbits, those parabolic plus minus. So you see, it's a whole zoo. So they are all, of course, examples of Virasoro Hamiltonian spaces. Maybe since I no longer have that much time, I spent much of it like trying to talk about some beautiful old stuff. So let me go to one of the results that I wanted to present. So this result concerns hyperbolic metrics on surfaces. And this is inspired by many physics papers. One of those papers is by Sarge, Schenker, and Stanford. So, but again, we try to understand some small piece in the beginning of that paper, which concerns geometry. Then they make contact to matrix models and God knows what. That we don't understand, but we may have some insight into geometry, which is going on. Now let sigma bar to be a compact, oriented, connected to manifolds, similar to the one that you see on the drawing. And again, I assume that the boundary is S1, but you can have many boundary components if you want. And now sigma will be the interior. So this will be now important to distinguish the compact surface and its interior. And here is the space N that we want to consider. So this will be a Riemannian matrix on the interior. And we require them to be hyperbolic, so their curvature is -1 or -2, depends on the literature that you're using. And then this rho. So on a collar near the boundary, you choose a boundary defining function. So the boundary is this rho equal to 0. So this is your S1, the boundary at infinity. And you require that on that collar, on this spin collar, if you multiply your metric by rho square, this will give you a nice Riemannian metric on the collar. In other words, your hyperbolic metric diverges when you go, so your end is at infinity. Incidentally, mathematicians and physicists invented different names for those hyperbolic ends. So mathematicians call them funnels, and physicists call them trumpets, which we find a little bit more poetic. Okay, and to finish the description of the space N, we divided by the connected component of the diffeomorphism group of the compact surface. And similar to what we were doing before, we require the restriction of phi to this to the boundary to be 1, right? So that's similar to what was happening before. So it's some kind of version of the moduli space of hyperbolic, complete hyperbolic metrics with this hyperbolic end for a surface with a boundary. So now I claim this is an example, and I will show you now the different ingredients, right? I should show you what is a moment map and what is a two-form. Interestingly enough, it's sort of easier, even though this is also involved, to show you what is a moment map. And here, remember, the moment map, in the case of loop groups, that was a rather easy story. Now, as you see from the slide, the story is somewhat more involved here. And I must say, so now what I'm presenting to you, maybe I don't do it in an optimal way because there are some miracles in projective geometry and miracles in hyperbolic geometry. But, and for me, they are still miracles, which means I probably don't understand the topic very well. But on the other hand, I think it's maybe more exciting to present it that way. And if there are specialists in those parts of geometry, you will tell me how stupid what I'm saying is. Okay, so we have a piece of our surface. So this is a piece of our surface. So this is this pink color. So the green line is a boundary of the surface. There is a boundary defining function rho. I introduce a coordinate theta along the boundary. So I have a local coordinate system on the collar, and the red lines are constant rho, constant boundary defining function lines. So on the collar, the hyperbolic metric looks like that, right? There is this term d theta square over rho square. Remember, there is a singularity in rho. So there is probably some coefficient a square of theta, and there are many, many more terms. For me, it will be only important this term. But there are many more terms. I do whatever, the Laurent expansion in rho of that metric. So then the first interesting claim, so that's a miracle of hyperbolic geometry. If you take a geodesic curvature of those red lines, of constant rho lines, you subtract 1 and you divide by rho square. So this guy has a limit when rho goes to 0. Right? It's not obvious, but that happens to be the case. So that's a miracle of this hyperbolic geometry, or of the hyperbolic geometry with hyperbolic end. And I denote this function by k of theta. So now we have two Lego blocks, this k of theta and this coefficient a. You see there is this a, which was a square was a coefficient in front of d theta square over rho square. And then the moment map is given by this funny formula, right? It's whatever, a square times k plus whatever, something which depends on a and on its theta derivatives. See, so that's our moment map or future moment map. Once I tell you what the symplectic form is. And now maybe, of course, you cannot appreciate the formula, that's just some unclear huge formula, but note that on the one hand, we have the action of diffeomorphisms on the metrics, right? So the metrics, you can transform them by diffeomorphisms very well. So the diffeomorphism of the closed surface, you can restrict it to the boundary, right? And on the boundary, you can act by this action with Schwarzian derivative. And the claim is that this map, right, this formula, it's equivariant under those actions, right? So this is a somewhat non-trivial fact. Here we even don't do any symplectic stuff, right? But we are claiming that there is an equivariance under those two actions. Okay, so that's one of the miracles that I wanted to show to you. It's interesting, strange. Probably, who knows, maybe if we knew better hyperbolic geometry and projective geometry, probably there is a way to make it obvious. From some higher point of view, it must be obvious. Obviously, when I present it like that, it sounds like a miracle. Now, what about symplectic form? So let me remind you that as usual in geometry, you can introduce orthonormal coframes, the Cartan moving frames, let's say alpha 1 and alpha 2. And given that, there is a unique one form which is called the spin connection, such that the Cartan's equations are verified. And if your metric H is hyperbolic, you can build these 2x2 metrics of one forms. And the fact that the metric is hyperbolic would be actually equivalent to the flatness of this SL2R connection. So that's some kind of classical stuff that you learn from the Cartan moving frame formalism. Note that this one form, so remember the metric has a singularity 1 over rho square. So the components of the coframe, they typically have a singularity something like 1 over rho. And it's easy to see that this omega would typically also has a pole on the boundary like 1 over rho. So A diverges at the boundary as 1 over rho. But now there is an interesting fact. So you can always find a diffeomorphism of the closed surface, which is equal to 1 at the boundary, such that there is this particular form of alpha 2 and omega. I mean, these are just formulas which don't say much, but the claim is that if this is the case, you can gauge transform your connection to something which is actually regular at the boundary. So you can you can choose in your class of metrics a metric such that your connection would be gauge equivalent to something regular. But if it's regular, then the Theobot form makes sense. So the 2 form is the Theobot form, but then again, this result is some kind of little bit of miracle, but probably that's because we don't understand it very well. Eventually, I think there will be a better formulation of that result, but well, one day probably. So this is our main motivating example. That's why we really got interested in it. And now I think since my time is almost up, maybe I skip the second result and I will say something about concluding remarks. As I said, there are many more open questions and there are some partial results. So of course, you may be wondering whether some kind of localization works. And one should say that in physics literature, there are localization calculations on quadroint orbits. So these are, of course, formal calculations because these are infinite dimensional spaces. There, for instance, for localization contributions, you get some operators. You need to have their Pfaffians or their determinants. So people do it, say, with zeta function regularization or something. So, for instance, yeah, there is an open question. Can you do some meaningful Dusterman-Heckman's theory in this story? So physicists pretend you can. To be honest, we don't know yet. I think mathematicians still have some room to discuss it and to make sense or whatever, approve or disapprove the physicist's results. One approach would be as follows. So the spaces to which now people apply localization, typically one can hope that they admit some kind of maybe global Darboux-Chads. Of course, if you have a global Darboux-Chad, maybe you can say that your infinite dimensional integral is some kind of Gaussian integral that you perhaps would be able to define probabilistically, like there are works, for instance, of Igor Frankl 40 years back, trying to define orbital integrals for coadjoint orbits of the loop group. And he does it probabilistically as Wiener measure integrals. So here, on some of the hyperbolic coadjoint orbits, there are global Darboux coordinates. so there is some work in progress I'm doing with checkers and humans. And maybe for hyperbolic metrics, it's not excluded, but maybe I want to stress that there is this Teichmüller orbit, and there all the indications that there should be the root coordinates, but it's absolutely not known. So there are physics calculations of Dustermaat-Heckman integrals, but there are no mathematical understanding of what's going on there. And finally, quantization commutes with reduction. I don't really know, but typically, for instance, for hyperbolic metrics, you expect the reduced spaces to be various versions of Teichmüller spaces. There are lots of work on quantization or different types of quantization of Teichmüller spaces. So why not? It's an interesting open question. I don't know whether it's going to be solved soon. Maybe in one of the next Poisson events, someone will speak about it. And I think it's midday. My time is up, and I thank you for your patience.
Thank you very much, Anton, for your magic formulas, many magic formulas. Are there any questions? Some questions? Okay.
I want to ask, is there some kind of possible finite dimensional description, like the classical Fock-Rossley or whatever, in this setting? Or is it possible? Or?
Yeah, probably. Depends on what. You mean, like, I didn't speak about it, but there is some sort of analog of group-valued moment map theory. That was the second result that I wanted to present. It is less perfect because there is no good normal subgroup. Instead, there is some kind of correspondence which always works one way from finite dimensional spaces to infinite dimensional ones. But to go back, you probably need some conditions on stabilizers. In other words, you don't get all Virasoro spaces, or maybe then you would need finite dimensional spaces with singularities to reproduce all of them, but it's more or less similar to what I showed in the case of loop groups, but it has some nuances.
So the classical moment maps are related to the Poisson sigma model. The LG moment maps are related to the Chern-Simons, the three-dimensional field theory. So which is the physics that?
Oh, I don't know. You see, like that. One thing. Let's say we derive this. The kind of our inspiration is the so-called two-dimensional Jakiv-Teitelbaum gravity. That's what the physicists are doing, and that's where we saw those spaces, or more or less those spaces, and that's our interpretation of what's going on there. Otherwise, I don't know if you think about Teichmüller spaces, right? There are Teichmüller TQFTs. I don't know, maybe that's also if you do it with a boundary, who knows? So the answers, as I said, that's probably related to this Q commutes with our question, right? So what is a quantum theory? How do you properly set it up? I don't know, but yeah, maybe Teichmüller TQFT of Anderson and Kashaev, or maybe something else.
I think this is somehow related to the two previous questions, but so these central extensions of loop groups are closely related to some two groups, which are finite dimensional when seen as two groups. And I was wondering if there is such an analog for these Virasoro extensions.
Yeah, that's a good question. Of course, there we see that PSL2R or the universal cover of SL2R, they play a major role, but not quite the same role. But also, I didn't mention there is a relation between loop groups and those Virasoro story, which is called the Dinfeld-Sokolov reduction. So there is some procedure which brings you from quadrant orbits of loops of SL2R or PSL2R to Virasoro quadrant orbits. Maybe that's the way to try to understand it. It depends whether this passage to two groups. I don't know whether anyone looked at how Dinfeld-Sokolov reduction would survive it. But maybe just it's a general phrase. But to summarize, this DFS1 story, it does resemble what we saw before, but all the time it has a lot of nuance and surprise. So that's why we find it exciting, and that's why I want to advertise it to you today.
There's one.
So I'm curious because you mentioned that convexity probably doesn't make sense. So can you just briefly point out why?
Because convexity usually, yeah, right. For that I have a relatively easy answer. You see, convexity usually takes place in the target of the moment map divided by the quadrant action, right? So here is the target of the moment map divided by the quadrant action. Of course, it has this funny structure, but it's mostly one-dimensional. Convexity in rank 1 case is not a super exciting thing. Maybe if one does the same, if one develops a similar story for those W algebras, instead of Verisora, right, it has some higher rank cousins called W algebras. They are no longer Lie algebras, but you can probably think of them as some kind of Poisson algebras. And then the target would be more complicated because here there is not much room. Like kind of something being convex means what? Something being a segment or, right.
We all need to think deeply. Thank you very much.
Thank you. Thank you for your attention.
Okay, yeah, I want to make an announcement since Anton is here. First, we have a special issue of the Journal of Geometry and Physics. Anton and I are editors of this special issue, and you'll get more information about this. Everyone, not only speakers, but all the participants are invited to contribute to this issue. And one more practical announcement is after this talk, after the talk that we have now, we will all go outside and take the picture in the sun, okay? The official picture. Now you can go and take a 2 minutes break.